here we go. This is formally on. Let's go. This is a brief lesson on limits. This is Unit 3. I bet you can't wait to get to Unit 6, where we start talking about sequences and series. Ugh. Okay, so 3, and 4, and 5 are going to be just pure calculus with um, uh, obviously differential calc in this chapter, and then integral calc in 4 and 5. It'll get interesting. So here we go. Let's talk a little bit about limits. So a limit, as you know, as you said, might be DNE, does not exist. That happens in a few situations. One, if, for example, this limit would not exist right here. If a function, right, as x approaches c, right, if the limit on both sides, right, from the left of c and from the right of c, if they're not equal, that limit doesn't exist. Okay, for a limit to exist, the left-handed limit and the right-handed limit have to be the same, right? So if I took this function and I dragged it down right here, right, then of course that limit exists because the left-handed side and the right-handed side, they agree. Another situation where limits may not exist are if you have some kind of discontinuity, right, like the one we had just mentioned, or in the example of, let's take this function, f of x equals 1 over x. Yeah, we got a problem here. This limit does not exist, so the limit as f of f as x approaches 0 from the left, well, that equals negative infinity, and the limit as x approaches 0 from the right of f of x, that equals positive infinity. And because they don't agree, we get a problem. Okay. There are a couple other situations where you might be fooled into thinking that a limit doesn't exist, but it actually does, and it just needs some algebraic manipulation. Let's see if we can look at an example like that. Oh, here we go. Very nice. Oh, we're still recording. Perfect. Okay, so initially, when you look at this, right, what's the initial step to seeing algebraically whether or not a limit exists? What do? You take 1, and what do? You just plug it in. You just plug it in and see, oh, let's see what happens. Well, if I plug 1 in here, I get 1 squared minus 1 over 1 minus 1, which is 0 over 0. That's, well, maybe, right? This is an indeterminate form. Do you remember L'Hopital's rule? The hospital? The French hospital rule? Of both, and do it again, and then just keep going, right? Now, we could do that here, or we could just use a little bit of simple algebra, and we'll realize that this function, which you may have been fooled into thinking was a quadratic, is actually just linear in nature if we cancel out that factor. And what you'll see is, after we cancel that out, now we're just taking the limit as x approaches 1 of x plus 1. And when you plug that in, what do you get? You get 2. Now, do you guys remember any calculus, like what's the derivative of x squared minus 1? 2x, right? And what's the derivative of x minus 1? 1, right? And if I plug a 1 in here, what do I get? I get 2 over 1, which is 2, which is the same thing I just got over here, right? So L'Hopital's rule can get you there as well if you get 0 over 0. So it's too easy. Let's look at a couple of examples. Here's that it does not exist. We just talked about this, a similar example. Here's a, yeah, no pun intended on that, too easy. Because the answer is 2. Yeah, thanks. Okay. Oh, okay. Maybe not. What kind of discontinuity is that? Do you remember? It's called a jump discontinuity. It's a jump discontinuity. Okay, this is an example of where the limit does not exist here. Here's where on the AP exam, and I think the IB exam might do this too. Oh, this is a terrible color on this. Say you take this. Let's say that you have this piecewise function, right? And f of x equals when x does not equal, let's say c, it equals the function. Let's just call it the rule, right? And when x equals c, let's say it's 7. Okay. Does the limit exist as x approaches c? It does, right? It's just a discontinuity, but as we approach from the left and from the right, I got to change colors again here. Okay, this one will probably work well. As I approach from the right, as I approach from the left, there is still a limit. We're just getting infinitesimally close to that. Doesn't mean that this value all of a sudden makes it not a limit. That makes it not what? Continuous or differentiable, right? So that's just a little start on limits. Let's take a look at a couple of homework problems. Here are some of the laws of limits. These are all pretty basic. The limit of one plus the limit of the other is the limit of one plus the other. The limit of the product of two functions is the same as the limit of each of those two functions multiplied together. It's just basic algebra rules here. We'll talk about Subway sandwiches later. This is the formal definition of limits. We'll talk about that later. I want to do a couple of homework problems. Ooh, here we go. What is this garbage? I don't want to do that one yet. Okay, here's a really good one. Number 6. It says the limit of the square root of x as x approaches 0. Does it exist? Explain your answer. Well, let's sketch square root of 0, right? Here's the square root of 0. Square root of x. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2, etc. Does the limit exist as x approaches 0? Well, that asks me two things. Does the limit exist from the right and from the left? And are they equal? Let's write this form. Well, from the right, let's look. What is the limit as x approaches 0 from the right? Well, it's 0. What is the limit as approaches, from the left? It doesn't exist, right? This limit does not exist as it approaches from the left. And because does not exist does not equal 0, this limit does not exist. So the limit as x approaches 0 of square root of x does not exist. Only a one-sided limit works there. All right, let's do maybe a couple more. Oh, yeah. Okay. Let's do one of these 3. I don't care which one. Graham, right? Yeah, you were looking awkwardly at me. Let's try one. Just pick one. B? Okay. So let's take the limit as x approaches 0 of sine x. Right, I can just use my rules that we briefly talked about. That was not meant to be a Beavis and Butthead laugh, but it kind of sounded that way. What's the limit as x approaches 0 of sine x? Where does it go to? Yeah, it goes to 0, right? Here's the graph of 2 periods of sine x. From both directions, it goes to 0. So that limit is 0. Okay, so I get 0. And what's the limit as x approaches 0 of e to the x? I could plug it in, or I could look at the graph. This point right here, and I plug in 0, I get 1. So is that a determinant form? Can I determine a value there? Yeah, 0 over 1 is 0. So the limit there is 0. Let's do one more maybe on the next page. Oh, gross. Do you remember back in the pre-calc days, the Bob, Bot, Sob? Don't do that, right? But they do apply in certain situations, right? If you're going off to infinity, like in this example here, right? If your limit is as x goes to infinity and you have polynomial over polynomial, you're just going to take highest term divided by highest term, and if they're the same, their coefficient ratio will be your limit. Kind of weird. Now just watch what I'm going to do here. I'm going to take the limit as x goes to infinity of 3 plus x over x plus 5. And what I want to do is I'm just going to multiply top and bottom by 1 over x. And watch what happens. I get 3 over x plus x over x, which is 1. And x over x, which is 1, plus 5 over x. So as I plug in infinity, what does this become? 0, right? That goes to 0. And what does this become? 0, and I get 1 over 1, which is 1. Filth. Cool. It's just algebraic manipulation. It's cool, filthy. Yeah, it's like a yeah, like a is it a what is that called? Filet o fish, yeah. Filet o fish. You've had a couple of those, haven't you, Zane? Oh, you just remember it. Okay. So look at this one. As x goes to infinity, yeah,